Okay, so let's get started over here. So the other day we started doing this one over here. All right. So we calculated the shear flows, and then we wanted to find what was the load on each one of the. So the top one we call them flanges, and then all the numbers were stiffeners. So I think we found the equation, we found the shear flows, then we did the top flange, we did the lower flange, and then I think then we did we do the number BF? Or yeah, that is what we did, the number BF, and that's where we stopped, no? Okay? So today we're gonna do the number, let's see, this one here, DKH, and then I'm just gonna give you the results for the other members so you can do on your own, okay? So I'm just gonna go to the detail for the member DKH now. So, all right. Okay, so let's sit down more space over here. All right, so let's do stiffener. DKH. Okay, so if I do a figure over here, for DKH, we had here the force F equal 12,000. This is 60. And we know that distance here is 200. This one is 100. And then as we did the other day, we're gonna on this side, we're gonna have Q1. And on this side, we're gonna have Q2. Okay, so if imagine this is a beam. So you want to find the deformation in this beam, let's say of the shear force, which is what we're doing now, the bending moment. What was the rule that you learned in statics, solid mechanics? Is that you need to make a cut every time is going to be a discontinuity on the loading, no? So if you start from here, where it's going to be discontinuity? Somewhere over here, no? So we need to make a cut before the discontinuity, right? So at least one or two cuts we need to do. Okay, so let's write this down. So we're calling let's say solid mechanics, but it must be solid statics as well. A cut must be made every time there is a discontinuity in the loading. So let's over here, we're going to make here one cut right before we get to the discontinuity. Okay, it can be anywhere. Okay, so let's say here we have D, K, H. Okay, so we do the first flipper diagram for, let's say, the first cut. This is D over here. As before, we're gonna start over here. We know Q1 is over here. And basically what we're trying to find is the force over here between the actual force between point F, let's say, and D and point K. Okay, so like in statics or solid mechanics, we do summation of forces. What do you get over here? You're going to get FDK minus Q1 times what will be the distance? S. Okay? So basically we find over here that FDK will be equal to Q1 times S. And I think we calculated Q1 to be equal to, so I think it's Q1 is 11.3. And Q2 we found to be equal. Is that one the negative? Negative. Yeah, okay, so let's have 257. Was negative. Was it negative? I think it was negative, no? Double check, but I think that one was the one negative. Okay, so this will give you basically that this is equal to 11.3 S. I mean, I don't have the pages with me, so from last time, I only have the PDF. So yeah, Q2 was minus 2.57. Okay. Okay, so now we pass over here and we need to know what's happening after point K. So basically what we need to do if you want is like a second cut to know what's happening afterwards. So let's say first cut over here. Second cut. We start from the same location, but this time we go past point K. And let's say we make the cut over here. Let's say this will be our point K over here. So now we're looking for the force at KH. So we're gonna have the Q1 over here. And now is when we need to be careful. So, okay, what else I need to put over here? I need to put the force of 4,000, and we know this is 60. So now I will ask you which way you want to do it. So we know FQ2 from the figure, all right? Okay, so over here should be going up, but you see on this side is going up, but we calculate it to be negative. So now we have the choice. Do you want to make it going up and then you will replace by the negative value, or do you want to make it going down and that way we just look the 2.57 of the magnitude? Basically, it's like a vector. No, vector has magnitude and direction. So you can put the direction on the figure, or you want to be the direction in the sign. So let's say I keep it on the sign. So if I put here then Q2, what should be the magnitude? What should be the magnitude for this Q2? negative 2.57, no? If I was doing here the arrow down, it would be positive 2.57. Okay, so you have the choice. I don't know which one is better. Oops. So here we do exactly the same thing. So we do summation of forces equal to 0 again. And okay, so we know the dimensions. So what are you gonna have? You're gonna have 200 Q1 Oh, sorry, this is, see, well, I should have done that on the figure, so I know this is positive. So then what should be, this one should be negative 200 Q1 plus FKH, maybe I should have started by this one. Minus Q2, what should be the distance where Q2 is applied? What is it? No, it's not S because S starts over there. So what should be? It should be S minus all that distance, no? So what is that? S minus 200, no? Okay? And now we don't have to forget this one. Plus the 4,000, we need to take the component of the 4,000 in one direction, in the vertical direction. So it will be cos 60, and all this stuff should be equal to 0. Sorry to make it that small, but I was running out of space. So now, if you substitute the Q1 by 11.3 and the Q2 by negative 2.57, you should get the equation minus 2.5709 S plus 771.28. And maybe before we do the figure, let's do one thing over here. If we look at this equation, FD should be equal to what? Should be equal to FDK at S equals 0, no? So that is, what is that value? 0. And if you remember, what did we find from the previous analysis is that when we did the distribution, what should be the load at the free end? 0, okay? So, makes sense. Now, we want to calculate what would be the load here at point K. So that is at what distance? So we could say Fk from this equation should be equal to what? Fdk at 200. So if you do that multiplication, 11.3 times 200, you should get 2,257.1 newtons. Okay, and if we do everything correct, I don't have a calculator here, but I will bet that this 2,257 should be equal really to what? To the 4,000 times cosine 60, no? Because it's the only force that is being put over there. Okay, now if we look over here, now from this point over here, what should be F sub K? F sub K should be what? F of KH at what point? At 200. And if we didn't do anything wrong, or you do the calculation, you're going to get over here that this load is 257.1 Newton. And similarly, the FH should be equal to FKH at 300. And if we did everything correct, that should be equal to 0, because as before, that will be the end of the lower flange, and that should be equal to 0. Okay, so basically, let me redo the figure over here very quick with less detail, but yeah, let's say this is D K H. We add here Q1, Q2, the force 4,000 at 60. So if we have to do the distribution, what does that mean? We go from 0 over here to FK to be equal to 2,257.1. Then what happens? Because of the load being applied at K, we see discontinuity on the loading. And this load goes over here now to be equal to 257.1. And then we know here that F of H is also 0. So what happens? This should be the load distribution in that member. Okay, so I think last time we did it for the stiffener BF, no? Oh, we didn't finish BF over here? Okay, so maybe go back over here to stiffener BF. Sorry for that. So let's say over here, oops. Yeah, so this is the notes from the other day. So if you want, don't do a continuation, go to the, so let's say going back. I didn't do the plot, going back to stiffener. Yeah, don't worry, you're gonna have space, okay? Let's say you have this just in one space, you just do the figure like, I do it small, so you have space to do it. Let's say you do this, so you have on this side Q3. Oh, sorry. Q4, I need to look also at this. So we had, okay, so I'm just saying you have this, and then, oh, go ahead.
If you go back to the previous scenario we were working on.
Do you want to hear?
Why are there two values for FK?
Okay, that's the whole thing. Remember, what do we say? When you need to make a cut, every time is going to be a discontinuity. So what's happening here is that when we look at this being DKH, when you just look at it from point D to point K, what's happening? This load over here has still not been applied to the beam, no, or to the stiffener. Correct? And then as soon as you get to this point, because the force is being applied, it's going to create a discontinuity over here. Does that make sense at all?
Yeah.
Okay. Very good question. So basically now going to this one, if I need now to, so this is B, F, and I think here you add the 5,000. So what did we find? We found the equation to be equal to, so I think you had here, the distribution will be this over here. Okay, well, you had over here 0, and this value here should be 5,000. Okay, so basically we go over here, just do this figure. See, f equal to 0, this equal to 5,000. Yes.
Can you zoom into
I mean, if I have to zoom here, Johnny, I have to zoom when I'm really bad, but maybe I'm gonna ask you to sit here at the front row next time. No, because I want to tell you, this is not bad. When we move to longer equation, I'm going to be running smaller. That's why I want to say that. That's the only reason. So if you have problems now reading, it's going to be more difficult later. Is that okay?
Yes.
So again, I want you to do this as a continuation of this, just for this at the end of what we did last lecture. Yeah? Okay. All right. And now I'm going to say, following a similar procedure for the other stiffeners, what you're going to get, so we're going to look first at the stiffener CJ. So this stiffener over here, let's see which one is on the figure. So we have, let's see which one is that one because I don't really remember. So we go back to the initial problem. Okay, so actually it's C. Okay, so is it discontinuity over here like the other one? So we have Q1 on one side. Q2. Q3. Okay, so if we follow a similar procedure for this one, what you're gonna get is you go from 0 to negative 923.1 and then to 0. So following your question, what is the biggest difference about this one? Why there is no change on the load for this one? It's because there is no force applied over here, no? Yeah? And I think the last stiffener will be stiffener JK, which is the one that is horizontal. So that one, what do we have for this one? We have Q1 going to the left. Q2 going to the right. And the 4,000 at the end. So you do the distribution of this one. You get 3,464.1. So this one will be okay. So basically that will be it. Okay, so now what I'm gonna do over here, I think I have videos, I will post one, but I'm gonna do something very quick over here for you to show you to check your answer. Again, you're not gonna be tested on this, but I think it's very useful to test your answers. Okay, so here we go. So what is PMAP? PMAP is a program of finite element. You might be familiar or not, so I'm not going to get in detail. This is not part of really the full class, but even though you have a project on this, but I give you the steps. But this really will help you a lot for you when you do the assignment to check your answers. So basically, it will almost help you to have the answer before, so that when you work it out, you can know if what you're doing is correct or not. All right, so let's just wait. Otherwise, I have videos about all this stuff online, really, that I could give you links, but I'm not too organized. Okay, so I'm not going to be waiting much more. Okay, so as we'll wait for this, I'm not going to keep waiting. I can go here. All right, so I don't know what to do here. Yeah, wait 10 more seconds. Okay. Okay, so basically you see how it is. I'm going to go very quick. Let's say we create the geometry. If I remember right, I think we have. So basically, I'm creating the geometry of this. All of them are 250, so I'm going to create points everywhere there is A, B, C, D, okay? So let's say 0, 2, 250, 500, 750. I do the same at the top, which is 300, 500, 250, and 0. So I give you the top. Now we need to create these two panels, which are located, I think, is at 100, at 500, and 750. All right. Control A, that centers the image. So you have all the points. Now we need to create the panels. So to create the panels, we're going to create surface, corners, and methods on points. So we created the points. After you see the points, you click on enter. So it should be the first panel over here. Second panel over here. Third panel over here. And let's say this panel over here. All right. Again, I'm not going to get in details. Materials here, really, you can put anything you want because we are not looking at deformations or stresses. So really, I'm just putting here aluminum, but you can put anything you want. It will not change anything. All right. So one material is enough. double click on it to make it active. Now we need to create two different material properties, one for the shear panels, which is called shear panel for the panels. But one over here simplifies the calculation. I'm not going to explain why I do this, just do it. All right, so another property is going to be to create the stiffness of the flanges. We say that those stiffer flanges are one force member, so rods are one force member that just get force on the actual direction. To simplify, put A equal to 1. Okay, cancel. So now I'm going to mesh this. So mesh control, size along curve, select all. Let's say I put here 25. No, element size 25, goes to 50. Okay, so that looks okay. Mesh, geometry, surface. I select all of them. We use the shear panels property. Here we go. Now we're going to mesh the stiffness, mesh geometry curves. Select all, okay. Property, okay, did it already. Property rows. All right. Now this might be needed or not, but I'm going to do it over here. Check, go into the notes, select all. Okay, preview. All right, so it was not needed, but I double check. Next, we're going to apply the load. Model, load, nodal. Can put a title or not that important. So at this node, if I remember right, okay, why it's not letting me select the node? Model, load, nodal. Oh, here we go. We had a force of negative 5,000. And then over here, we had 4,000 times sine 60 for the x. And negative 4,000 cos 60. So you see the 4,000. Now we need to apply the boundary condition or the support condition, model constraint, on curve, whatever, fix. Okay. Cancel, file, save as. This PC, desktop, new. Them. So basically, I'm not going to save these files. Okay, if you want it, you're going to have to create your own file. I'm not going to give you those files. You see, I don't even save it for me. So model 1, even though I'm sure I have on my computer a similar one somewhere. Anyway, so this now we apply here to run, create new static solution. Now you pray so you don't get an error. If you get an error, sometimes it's easier just to restart from 0. So we now have errors, F5, criteria, deform. We're going to look at the shear force first. I know I'm going fast because I don't want to. Okay, what happened here? Okay. Okay. So okay, that's too big, but let's see what do we have here for these values. That was negative 2.67. Okay, it's giving positive because it can be a different sign convention for this one. I think for this one we had 11.3 now. Then what was Q3? I don't remember, but Q3 was how much? 6.67, 23.3, so 6.67 about now, 6.6, about 23.3. All right. So Control A, now do F5 again. I'm going to put this time bin diagram. Okay, I'm going to go now to the elements of the actual roads. So road actual force. Okay. And now you see that if we look at the deformation of the, if I eliminate here the shear property, and if you want some of the geometry. You see, this was the distribution on the top flange. This would be the distribution on the lower flange. This would be the one on this stiffener, and this stiffener. Remember here, it was going from 0 to 5,000, no? Okay. Now you want me to show you a little trick to visualize this a little bit better. I'm just going to do it for one. So you can go here to groups. So let's say we do here let's do the top flange, okay? You can create a group just for the top flange. Oops. Okay. Now you go to group, elements, ID, method, on curve, select the top curves. Okay. Now you can come to the group, double click on double group, right click, show active group, and then we just show it to you. I mean, it also took the shear, but that will be the distribution, okay? So at least it will give you an idea. Oh, just one thing, just notice over here, the value is giving you here is 9,952, and the one we found in the calculation was probably, it's going to be higher than that, is 10,323. Okay, so what is the difference? Is this one wrong? It's not that it's wrong. What happened is that the accuracy so the accuracy depends on the value of the mesh size. So over here, this value that is giving you the average value between the value at this node over here and at this node over here. If you make it smaller, then this value starts going up, no? And if you make it very small, then you will get the 10,000. But it will give you an idea if you are on the correct range. Okay? So you see, this took us probably what? Less than 10 minutes, and it will give you a pretty good answer, no? All right? So let's keep going now with the rest. Okay, so let's go over here. So in most aircraft, not to say all of them, most of the panels are rectangular. So if they are rectangular, what do we know? We know that the shear flow over here, we say we use. See, now this is smaller. Okay, because I zoom in, maybe not on that. So we say that the shear flow is basically constant in the four edges of the rectangular panel, no? Okay, but what happens if it's not rectangular? But what happens to the shear flow Q if the panel is, instead of saying not rectangular, let's say that is tapered. Okay, so that's actually a lot of work for not too much. This stuff of the tapered panels, but let's just do it. Wow, not that bad. Okay, so this, let's look at tapered panels. Tapered shear panels. So let's look at the geometry of a general taper panel. So this will be a shear panel that is taper. So obviously in order to study this one, so let's see. All right, if we do the continuation, we have this. So let's say this will be defined within a coordinate system y and x. Okay, so this edge, we're going to call it HL. So HL is for H long. So L stands for long. So obviously we use the same notation. This side here will be H sub S, S for short. Now, this panel over here, we're going to call this angle here theta sub B. B stands for bottom edge of the panel. And I'm going to put here theta sub T, so that T stands for top edge of the panel. So assuming that all shear flows are constant along the edges. So, oh, did I close it? No, it's here. Okay, so that's a good thing over here that I kept it. So this final element jelly is going to give you better results that what you will get, by hand calculation. Remember, you have many assumptions when you do hand calculations. So let's see if I come over here. All right. I mean, we had reasonably pretty good values, no? But at these, oops, at 8, xy top, okay. Are these values over here constant? They are not constant, no? There are small variations, no? Okay. I mean, here they are almost constant, but really in real life, you can imagine that because as this is deforming, all right, really these panels becomes not taper, no? Due to the deformation of the forces. Initially, they are exactly as a rectangle, but as they deform, they can become taper, no? So you see, but in this case, if the deformation is small, you see there's no big variations at all. All right. But again, so that's one assumption. So if we assume that for the one that's already tapered, they are all constants, we're gonna have here the new figure. We have 2 over here, 1 over here. Do this, this, and this. So you have over here Q long, Q short. You remember, same sign convention over here for the shears, okay, up and down. This will be here, we're gonna call this one Q top. And now this one here should be Q bottom. Okay, remember that our sign convention we're using is this one over here, okay? For Q. Okay. So if from this element we do the summation of forces on the x direction, and we also need to use the top figure. So if you do a calculation, you're gonna get that Q top. So what should be the force? The force should be equal to the length, no? Of this one over here. So it should give you Q of, oh, I forgot to do one thing on the top figure, otherwise we'll never understand it. So on this top figure, this is x of s. This is the length of the panel. And all this stuff then will be x of l. Okay, so then the force will be QL cosine theta top cosine theta top minus QB L cos theta bottom cos theta bottom equal to 0. So over here, the math ends up being very simple because all this will cancel. So basically we get, which makes sense, that Q top L minus QB L equal to 0. Or this will just give you that QT L equal QBL. Or this will give you that Q top equal to Q bottom. And since they're equal, I'm going to say that this, I'm going to use rotation Q hat. Here the derivation is not that important. The important is at the end of the conclusion. So we did the summation on the x direction. Well, we're going to do exactly the same thing, but the summation on the y direction. If we do the summation on the y direction, we're going to get the equation minus Q short H sub S plus Q long H sub L plus Q top, but you know that Q top is equal to Q hat. Can do that maybe at the end. L over cos theta top. Before we had cosine theta top, this time is going to be sine top minus Q sub L, L over cosine theta bottom, sine theta bottom equal to 0. And again, this should be the, sorry, this should not be Q hat, this should be Q bottom. And this is Q hat. So if we simplify, we get Q L H sub L minus QS H sub S plus Q hat L tangent theta top minus Q hat L tangent theta B equal to 0, which will give you that Q sub L will be equal to Q sub S HS divided by H sub L minus Q hat L tangent theta T minus L tangent theta bottom and it can be shown that from geometry this is equal to H sub L H sub S over H sub L. So basically, and again, don't worry about the derivations. The derivation is not important. So at the end, we get Q sub L equal to Q sub S H sub S H sub L minus Q hat H sub L minus H sub S over H sub L. Okay, so we do summation of forces, X, Y, and then we need to do the summation of moments about point A. I'm going to tell you where point A is now. So point A is located over here on the panel. Is this one over here. So we do here the equation. This is going to give us Q sub L H sub L times L minus Q hat of L over cosine theta top times cosine theta top H sub S. So basically, just to explain very quick, if you go about point S, you neglect the shear flow going through this H, and this H, no? So you only have two terms, this one and this one. That's what we have over here. So basically, this will give you the second equation, Q hat equal to QL H over L H over S. Almost done. So now what we are left to do is to substitute in equation B into A will give us what? Q sub L equal Q sub S, H sub S, H over L minus the Q hat becomes Q sub L, H sub L, H over S times H of L minus H of S over H of L, which will give you that Q long equal to Q short H sub S over H sub L squared. Equation C. And finally, let me go to the next page. Substituting C into B. So you see this one, this derivation I almost have to copy because it's not as complicated, it's just statics, but it's easy to do a mistake. So we have Q hat equal to QL H long H short. So this will become what? Q short HS over H sub L square H sub L over S sub H. So that at the end we have Q hat equal to QS H sub S H over L. Right. So in summary, this is really all you need. In summary, you see if Q short side is considered as the unknown shear flow, okay, so if you remember, maybe I'm going to do two figures over here. One, two over here. And then, okay. So remember the first figure we did was what? We did this figure over here, no? So this I'm just going to recopy exactly that one. So it should be QS, Q long, Q bottom, Q top. Okay, so this is our original knowns, but we know that Basically, if we take Q sub S as our unknown, we should be able to rewrite all the other ages in function of Q sub S. So basically, what do we do over here? We know that Q long was equal to what? We derived the expression on the previous page that this is equal to Q short H sub S over H sub L long. That was equation C. Yep. Now, what do we know? We know that what is the other thing that we said is that from equation A, if I remember right, 3, 4, what is my equation A? Yes, from that equation A, from the first equation, we know Q top equal Q bottom equal Q hat. Okay, and we say that Q hat over here. Okay, so we can reverse the order over here. We have Q. So this will be Q hat over here, Q hat over here, where Q hat is equal to what? Will be equal to Q short. We have it over here, Q short. H sub S over H sub L. Is it a square or not square? Let me double check here something. Okay, that's that what we do over here. It should be this equation here. Okay, so basically, Charlie, I don't like for exams, but I don't like a page, but this will be given to you, or I will give it to you on the same day. So basically, you don't need to do the whole derivation. You can have this little sketch over here. Okay. So one, this should be something that will be given to you. Okay, so we're going to do a direct application of the problem, and that will be it for today. So example. And I know this example comes from Dr. Radoska notes. So let's see. On this case, 1, 2, 3. So let's say this 1, 2, and 3 over here. Up 2 over here. So it's taper. All right. This will be 1, 2, 3, 4. We have here fourth os 5,000 newtons. The height of the short side, so you want H sub S will be equal to 0.45 and H long equal to 0.60. And the length, the overall length, L, is 1 meter. So the question is obviously to determine the shear flows in the paper panel. Okay, so basically what I want to do is using this figure over here, okay? Just direct application. So from figure, what am I going to get is that Q12 equal to Q long, 1,2 equal to Q long, Q34 equal to Q short, Q14 equal to the Q hat, and Q23 equal to the Q hat. So what do we say? Considering Q sub S in this case, so Q sub S is what? Q34 as the unknown in order to get the other ones. Okay, what can we do on member 3-4? What do we have on 3-4? Remember, this is the unknown that we need to find. So that we know about 3-4. That's where the load is applied. Okay, when you look at this figure here, this should be here Q short. So we do the summation of forces equal to 0 in that direction. So what are we going to get? Q short times H sub S minus 5,000 equal to 0, which means Q sub S will be equal to 5,000. What is H sub S? (0.45). So this will give you that Q sub S. Didn't do any mistake here. Is 11,111 newtons per meter. Well, let me do here maybe another small figure for, I think, for the Q sub S. for clarification. So 1, 2, 3, 4. So we have here Q sub S, Q long, Q hat is called Q top. Q hat equal to Q bottom. Okay, so finally we can say using the relations in page 5. So basically, which relation am I talking? I'm talking about these ones over here. Okay. What are we gonna get? We're gonna get Q long equal Q12 equal to QS times A sub S over H sub long square. So if you do the mathematics, this should give you 6,249.9375 newtons per meter. Q bottom will be equal to Q32 equal to Q sub S A sub S over A sub L, which is also equal to the Q sub top, which is Q14, and both of these one will give you 8,333.25 newtons per meter. So that's the final image. What else? We need to look at the figure. What we have is 1, 2, 3, 4. So we have here Q short equal to 1, 1, 1, 1, 1. We are equal to 8,333.25. 8,333.25. And then this one over here, Q long, 6,249.94. So basically, you see that the shear distribution along the edges is definitely not constant, no? Sorry, the overall is not constant, yes.
How did you determine this direction? Where the executive?
What do you mean the direction?
The direction of the shear flows.
No, I just used what did I say on this page? Remember, I've always been using this sign conventional here. What is that page? Even when we did the, okay, here we go. I think this page is gonna be. No, it's not that page. Yeah, you see, even in the problems we did before, I always been using the SAS convention, no? So that's the only thing I'm done.
Okay.
Okay. Okay, so now we did. Is for side.
Oh, no, that's on hand.
Oh.
Do tomorrow.
Yeah, guys, that's the assignment that is in Canvas. Forget about it, okay? Let me